So let's look at our properties of bases. We've already looked at acids. Let's look at bases. Okay, bases will react with acids to form salt and water in a neutralization reaction. Review from our reactions unit. Bases do have a bitter taste, and they feel slippery. So have you ever gone on a cleaning spree? Maybe your parent, whoever you live with, mom, dad, aunt, uncle, grandmother, whoever you live with, said, you know what? You are not going out to the movies with your friends tonight until that bathroom is clean. So you go on a cleaning spree and you spend a significant amount of time cleaning. Well, cleaning products are bases. So the reason your hands feel slippery when you're finished cleaning is because you've had your hand in a basic product, and that's where that is. If you've ever dropped some gas on your hand while you were pumping gas, you may have noticed it also felt slippery as well. Even after you washed your hands, you may have still felt a little bit slippery. Okay, but another example of a base. Now, bases are made of hydroxide ions, so they are ionic. So strong bases are going to dissociate. Remember, ionic compounds dissociate completely in water. And some examples of strong bases. These are the strong bases that you need to know. Group 1A hydroxides. Strontium, barium, and calcium. And if you'll think back to our reactions unit, we saw that hydroxides are insoluble except, and there were some exceptions there. All right, 1A hydroxides, strontium and barium, and we're going to add calcium. Calcium is also a strong base. It will dissociate completely in water. Weak bases do not dissociate completely in water. So they will form some ions, but not all ions. So strong bases will form all ions, weak bases will form some, but not all. So let's take a look at our theories of bases. And again, we're only going to look at two of the theories. There are more than two, but we're going to stick with the two. And our first one is an Arrhenius base. And an Arrhenius base is going to produce hydroxide ions in water. All right, and for example, we can look at sodium hydroxide. So if I was to place sodium hydroxide in water, I will get all sodium ions and all hydroxide ions. And I know I will get all ions because sodium is in group 1A, and group 1A are strong bases. So this will go to completion, meaning we would have no more sodium hydroxide left. We would have all ions. And then we also have Bronsted-Lowry bases. Now, if you'll remember, Bronsted-Lowry acids are proton donors. So a Bronsted-Lowry base is going to be a proton acceptor. So let's look at an example. All right, if I have H2PO4 2- and I put that in water, H2PO4 2- and I put that in water. Let's say this H2 donates a proton to the water. So if I donate a proton, I get 1 hydrogen, and that is going to be HPO4 minus. And then I am creating H3O plus. So the proton donor, this H2 was the acid. The acceptor, water, was accepting the base, or the proton, excuse me, water was accepting the proton. So water in this case is acting as the base. Now, it is possible for something to act as an acid and as a base, and we call those amphoteric. So something that can act as an acid or a base is amphoteric. So let's take this HPO4 minus, and let's add it to water. Okay, water can donate a hydrogen back. If I start with 1 hydrogen, I now have 2. The PO4 is still there. And when I add, and this is going to be, I've got my 3. Okay, so when I donate my hydrogen, I'm sorry guys, I was thinking. All right, so when I donate my hydrogen, this is H. Oh, okay. So here's where I went wrong. I have my charges wrong, and this is why I'm all confused over here. Okay. This is a minus. I'm so sorry. Can we revert? This is why I'm confused over here, because I just messed up my charges. All right, this is H2PO4 minus to form HPO4 2 minus. Can we go back and make that quick adjustment? So this HPO4 is a 2 minus, and this is why I was confused in my head and I had to stop and think about it for a quick second. All right, I had my charges messed up. So when water donates a hydrogen, I get 2 hydrogens, and this PO4 2 minus becomes a minus, and my water loses a hydrogen to form hydroxide ions. So water in this case is now donating, it is acting as the acid. HPO4 2 minus is acting as the base because it is accepting. So what does water form? It forms hydroxide. So we call that the conjugate base. And HPO4 2 minus forms H2PO4, and so we call that the conjugate acid. So a base forms a conjugate acid, an acid forms a conjugate base, and if we were to look up here at this first example, my acid, H2PO4 minus, donates a hydrogen. So it forms, when I get rid of a hydrogen, it forms this HPO4 2 minus, which is the conjugate base. And my water became H3O plus, which is the conjugate acid. So again, my acid is forming the conjugate base. My base is forming the conjugate acid. Water is amphoteric. It can act as a base or an acid. And this whole concept right here is the concept behind our dreaded unit of buffers, where rumors fly high and all around, and most of them are true, but the reality is the unit is really not that bad, okay? This right here really isn't that bad, is it? Water can accept a proton, all right, or it can donate a proton, all right, and we are forming something that is acidic or something that is basic.